Hey guys, so let's talk about the last bit of the puzzle here, where we're going to talk about trigonometric substitution under the series of tackling quadratics, okay? So, before we even begin this topic, we need to make sure we have a clear motivation of why we want to use this, and how is trigonometry any helpful apart from just being hideous to begin with, okay? So a lot of people feel intimidated with this. I'm trying to simplify, whatever you need to know in order to solve these expressions and all that. So before we do that, we need to make sure we remember a bunch of facts, okay? And I'll show you how to use those facts later. So the fact that you got to see is there are supposed to be like two identities that you need to remember, okay? The first one being the world famous sine squared x plus cos squared x equals to 1. So you know this identity is always going to hold true. Now the second identity that you need to remember is derived from this identity itself. So what if you divide this whole equation by cos squared? So when you divide this whole equation by cos squared, what you're going to get is tan squared x plus 1 equals to secant squared x. Okay? And that's pretty much the two that you need to remember. The third one is nothing but a rearrangement of the second. So the rearrangement of the second is just going to tell you tan squared x equals to secant squared x minus 1. So what we're trying to tackle here is I'm going to write the first identity in a rearranged form as well. Okay, so that you guys can actually have a better way of thinking about this whole situation. The first equation could be rearranged by sending either sine or cos squared to the right side. Okay, I'm going to write one variant. You could use any other ones if you want. I'm going to move the sign over. So my identity will look as cos squared x equals to 1 minus sine squared x. So the reason why I wrote them like this is for you to be able to identify the basically the three standard forms that you can see an arrangement of a quadratic. Okay, and those forms are going to be this x squared plus a constant squared, which kind of resembles like this form. A constant could be represented by 1. Okay, so I'm going to try to write the corresponding things that they show you. So x squared plus some constant squared resembles like tan squared plus something, right? And then if you think about the top, that will be like, at the bottom you have a secant squared minus 1. So you have x squared minus some constant squared. That should resemble the secant squared x minus 1. That is resembling tan squared x plus 1. Now on the top, what you were expecting is 1 minus a squared, so you have a squared minus x squared. So these are the three possible arrangements you can ever encounter in your life when you're doing integrals for like trig substitution. Okay, so these are the arrangements that we're going to work towards, and that's what we're going to use as our evidence. Okay, now when is this helpful? Trig substitution is helpful when you're actually solving like this. So when you see square root of x squared plus minus a squared, right, all of that stuff, or you see 1 over x squared plus minus a squared. So now a clear disclaimer that you see here, what you need is something squared plus a constant in essence, right? So something squared plus a constant is nothing but the other words of the complete square form. Remember, in the previous videos when we talked about it, you knew in order to be able to tackle these things, you need to make sure that whenever you see a quadratic, you have to convert them into a factored form or a completed square form, either one of those. If you can factor it, you got to go to the process of partial fraction decomposition. But if you can't factor it, you have to complete the squares and then follow trig substitution. So now we're going to come back here and tell you why trig substitution works the way it's supposed to. Okay, so what I'm trying to do, I'm going to start with a very basic example. Okay, all I want to do is I want to simplify an expression. Okay, I am taking this integral 1 over x squared plus 4, okay, dx. Now the motivation here is I want one single term instead of, the x squared plus 4. I want to reduce into one single term. And this would help me out because, having one single terms are kind of slightly easier to evaluate than having this weird fraction at the bottom. And same thing goes for the square roots. When you have square roots, you want to make sure that you have something simpler in the expression to help you out. Now, I want to go with this motivation. And I also happen to know certain identities that can help me out. Okay? So what I wanted to do though is have to relate back to one of these cases that I mentioned on top and see, because what this does, this identity turns something minus sine squared into one single thing. This is cos. This identity turns tan squared plus something into one single thing, that is a secant. This identity tells something squared minus 1 into this thing. So what kind of arrangement are we looking at? We're looking at sum squared plus a constant. So sum squared plus a constant. This tells me that, okay, I'm leaning more towards tan. Okay, this is where you have to see the motivation of what trig substitution you should make. Okay, so let's start off with this, right? So what if, I'm going to ask myself a question. What if that x squared that I have, okay, was, 4 tan squared? How the hell did I just think of a 4 tan squared? Because what I'm aiming towards is to form a tan squared plus 1. Okay, so if I put a 4 tan squared, I can see that I can factor out a 4 from them, and then I can go ahead and solve this expression, right? So what if my x squared is 4 tan squared? This expression will become, this 4 tan squared at the bottom plus 4, which could be factored out. So you have tan squared x plus 1. And tan squared x plus 1 is just secant squared x. So you're going to end up eventually with 4 secant squared x. The reason why I didn't type any numerators right now is because whenever we're doing substitution, always remember you have to change this guy as well, right? So we're introducing a new variable. We can't say x squared equals to 4 tan squared x. We have to cook up a new variable. So instead of asking it to be 4 tan squared x, I'm going to ask it to be 4 tan squared t. Okay, some new variable t. From there, basically the substitution that you're making in simple terms is that x needs to be square root of that whole size, right? So if you take the square root of that thing, you're going to get 2 tan t. Okay, this is our substitution. Just like how you did in the u substitution, you choose u to be that. In this case, you'll choose your x to be something. Okay, so you choose x to be 2 tan t. In result, you're going to get x squared to be 4 tan squared t. And then you're going to have all of these expressions turn out very nice. So I'm going to get this to be, t, and then secant squared t. Nice. So now, because our variable starting was with dx, now I have to convert it back into dt, right? So how do you find dt from that? Is by taking the derivative of this expression. So when you do so, you get dx over dt of this guy, of the x expression. You get 2 times derivative of tangent t is secant squared t. And from there, you can say dx is nothing but 2 secant squared t dt. Nice. So the numerator was dx. In this case, it'll become 2 secant squared dt. And then 2 secant squared t dt. And 2 secant squared t dt. So this is how you will gradually simplify the expression. Okay. So when we got to that motivation, we converted the bottom into a single thing, and we just literally plugged in what the top dx would be. We see something magical happening right away. Okay, you see this secant squared t and this secant squared t can cancel each other out. So essentially what you'll be left with is you can factor the 2 over 4, which is just 1/2 integral of dt, which could be easily solved to be, t over 2 plus c. Nice. So now, just like any substitution problem, when you're done solving the integral, you got to plug in back what you chose to be your t. Okay, so let's take a second here. We chose our x to be 2 tangent of t. So tangent of t is just x over 2. So t is nothing but tan inverse of x over 2, right? So when you can see that, you plug it in there, this expression will just have the final result to be tan inverse of x over 2 over 2 plus c. And this is the answer. So this thing could be easily solved into this expression down here. So the multiple things that I want you to observe to begin with first is that every time, first of all, you got to see which model fits the scenario. Okay, it's going to be something squared plus 4. Okay, something squared plus some constant. If it's something squared plus a constant, then you're going to go lean towards the tangent side. If you have something constant minus x squared, like if in this case was just like 4 minus x squared, the answer will be different. Because to make 4 minus x squared into one single term, you would want to lean towards the sign, right? So that would be the motivation here. And then if you have, let's say, the other way, where you have x squared minus 4, you know, some x squared minus the constant, then you want to lean towards secant, because then something squared minus 1, which should be secant, is reduced to be tan. So knowing this, and then knowing that every time when you plug it in, this simplification will become something that you already know, right? Because we're fixing what we're going to input, we're going to put tan, then we know every time the bottom is going to be resolved into a secant. If you're picking that we got to plug in sine, the resolve will always be equals to cos squared. If we're picking something to put secant, we know the thing will resolve to be tan. So using that information, what I've done is I've compiled my notes. My notes are going to condense all of the information and will give you, a faster way of approaching these problems. So the notes are here, right here. So the motivation when to use is to tackle problems which have x squared plus a squared or x squared plus a squared inside a square root, either in the numerator or in the denominator. Okay, this method would eventually get rid of the two terms being added up and change it into one single term, and that's the motivation, right? The useful things that you need to remember are just going to be rearranged in this way. This is the simplest form. The simpler forms in this, and the complicated forms are on the right. So if you have 1 minus something squared, if you choose it to be sine, that will be resolved into a cos. If you have 1 plus something squared, you choose it to be a tan, and that will be resolved to a secant squared. Okay? But if you have something squared minus 1, so you will just go back and plug it in, and you'll resolve to tan. So the basic rules here are given in this bold. If you can follow this, you'll be able to find it faster. Whenever you see x squared plus a constant squared, okay, so in this case, we saw x plus 4, right? In this case, you can write this to be x squared plus 2 squared. So essentially, a was 2, right? But what if you see nothing like that? Let's say you see x squared plus 3. You can write this as x squared plus square root of 3 whole squared. So in this case, what you have to see is essence is that a is square root of 3. Okay, let's say you see 5 minus x squared. Then if you see 5 minus x squared, it should resemble the form of a squared minus x squared. So in this case, you can write this as square root of 5 whole squared minus x squared. Okay, in this case, a is basically square root of 5. So you got to identify this, and you'll get better at it once you actually solve problems, right? Once you see this, this is the basic condensed notes. You can memorize it, or you can remember this, or follow with the motivation. Completely up to you. Whenever you see an x squared plus a squared, substitute x as the a that you identify by looking at the pattern by eyeballing it times tan t. When you do that substitution, your dx will convert into this. Okay, every single time. Every single time when you pick this kind of thing, it will always be this. And the expression that you began with, the x squared plus a squared, could be broken down into a very simple expression, which is just a squared secant squared t. Okay, so these are just like condensing what we've done before. You can always solve any problem using the motivation, or else you can remember these rules to solve it faster. Okay, completely okay. Whenever you see x squared minus a squared, that resembles this guy, right? Something squared minus the a squared. So you will always pick your x to be a secant t every single time. When you substitute your a secant t like that, your dx will become a tan t secant t, because that's the derivative of secant, right? So that's also fixed, and then whatever you started off will be resolved into a squared tan squared t. And that's easy. Okay, the last exceptional case is when you have x squared plus a squared, you have x squared minus a squared. Now you have to flip them. You have a squared minus x squared. right? When you have a squared minus x squared, the possibility is you're leaning towards sine, because something minus something squared will get you this thing. Okay, when you plug in x equals to a sine t, your dx will automatically become this every single time, and your expression will be resolved into this. Okay, so this is like a lot of information right now to kind of like see without examples. So let's go over and look over examples. Okay, so let's cook up another equation here. Let's say I want to find the integral of 1 minus x squared. Very simple. Let's start out very simple. When you see this, the first line of defense would be to try to like, factor it into 1 plus square root of x, and then, all the way, and then you just do the basic partial fraction. Or you can do u substitution, but u substitution won't work here. So let's go with trig substitution. In this case, what I'm encountering is a form of something squared minus the x squared. Okay, so the rules are telling me, because if I see that there, if I'm seeing this, I want to substitute my x as a sine t. All I got to do is identify what my a is. In this case, you can write it as 1 squared minus x squared. So in this case, my a is just 1. So the substitution will be like x equals to 1 sine t. And then by the rules, I always know that my dx will always be a cos t dt. And this happens to be, just 1. So dx will be 1 cos t dt. When we plug it back in, my integral will become 1 cos t dt over, I know my expression that I began with, the 1 minus x squared t, in this case, will be resolved to this, a squared cos squared t. So I know this rule. Knowing this, the bottom could be easily written as, a, which is 1, cos square t, right? And now the magic will happen. In this case, the magic is that you get rid of this cos. You basically have integral of, 1 over cos t, which could be written as integral of secant t dt. And this particular one is a standard integral. Okay, this particular question has a standard integral. What you can do is you can actually find and Google it up. So I'm going to leave it here. The point was to actually demonstrate, just how do you get to the simpler form. The secant t integral, there's multiple ways of actually solving it. You can learn how to solve it, or you can actually learn the form that is going to be the answer of this. Okay, that was just a motivation here. Now, what if I have this kind of expression? Let's say, same thing, but inside a square root. Okay, it doesn't change the fact. It doesn't change anything. Everything else will stay the same. The form here again resembles the same that we had before. So a squared minus x squared form. So I would choose my a to be 1 in this case because it's 1. And my substitution will be x must be equals to 1 sine t. That will lead up to my dx being 1 cos t dt, right? And then this 1 minus x squared with the substitution could be resolved into 1 cos t whole squared, and that's it. And now when we plug everything in, the dx will become 1 cos t dt over square root of 1 cos square t. Because square root of a squared is just going to be that, so I'm going to be left with cos t over cos t dt. Magic happens, this goes away. And then you're going to be left with dt, which happens to be t plus c. That's the integral. And now we're going to substitute it back in. So in this case, I chose that to be my starting expression. So if that's the case, then I can say if x equals to 1 sine t equals to x over 1, or just x, right? And then in this case, t could be written as sine inverse of x over 1. Okay, and that's where you plug it in here. So the final expression will just be sine inverse of x plus c. Many of you guys saw it coming because some people also remember this being the, the standard integral, because derivative of inverse sine is that. So integral of this is sine inverse of x. So you already know this, but this could be solved using trig substitution as well. Okay, so those were the two examples, very straightforward. Let's go a bit complicated here. The complicated example will be when you see something weird happening. So let's go here and I'll try to give you this integral that will just be this guy. What would be the best way to start off? You know, just thinking about it. How about I give you an example on a quadratic first, okay? Just like a quadratic that could actually, you know, use trig substitution. So, you know, whenever you want to see like trig substitution in action, what you got to focus is something that looks like a completed square, right? So we got to pick up a thing that we cannot actually, you know, factor. So let's see. I'm going to stick back to the one that we started off the argument with. The x squared plus 2x plus 2. Okay, x squared plus 2x plus 1 was factorable, but x squared plus 2x plus 2 is not factorable, right? You can't factor it, so you have to complete the squares. So first of all, let's complete the squares. So when you see x squared plus 2x, I'm going to try to do that in a different color. So you know that that process is not a part of trig substitution, but it's something that you need in order to apply trig substitution, okay? So I'm going to say x squared plus 2x plus 2 could be written as in the template of x squared. Coefficient is 1. We're good. So we can start. Go ahead, do that. So 2 times x times something plus that thing squared minus that thing squared and then plus the 2, right? So in this case, you got to match the coefficients of this guy with this. And what number do you think we need to multiply this by? In order to get 2x, we're going to multiply by 1. So that bracket will also have 1. This bracket will also have 1. This, however, is a complete square of x plus 1. This could be resolved again into a single number, which happens to be, you know, minus 1 plus 1. So that's just that. 1. So this. The integral in the new form, in the, you know, the completed square form, will look like this. Now, when you see something like this, you know there's a traditional way. The traditional way to solve these kind of things is, first of all, making it look exactly like how you want it. So you want it to be something squared, not x plus 1 squared. You want to make sure that thing is a single entity, right? So the single entity, what I'm going to do is u substitution. So if I let u equals to x, that's just like an intermediate step in the middle. When you do that, your du will be equals to dx. Knowing this, your new integral will just be dx over u squared plus 1. And this is looking nice. This could be actually solved by trig substitution, okay? So when you do a trig substitution, what form are you looking at? You're looking at x squared plus a squared, right? In which case a is 1, because in this case this is just 1, right? So what you have to do is you have to substitute. In this case you have to substitute as tan, right? So x needs to be a tan t as per the rules. So x will just be 1 tan t. From there you can find dx. That's also the rule. That's going to be secant squared t dt every single time. When you're going to get this, let's plug it back in. We're going to get secant squared t dt. At the bottom, because of that substitution that you made, the bottom will always be resolved to this guy, as you can see. So in our case, that will just be, you know, the a squared secant squared t. A is going to be 1, so we're just basically ending with secant squared t at the bottom. And again, the magic happens. This can get rid of it. So you basically have this with dt, which happens to be t plus c. So a lot of integrals are very easy to resolve after the simplification, right? So now in this case, our expression was x equals to tan t. So t equals to tan inverse of x. Hold up. My bad. Actually, we began with the u, right? So this will have to be u. This looks like a form, so I'm going to substitute u, and then du. Top will have du. My bad. So we got this, and then when we simplify the whole expression, we're going to get this to be u as well. So tan inverse of u. So the answer so far is tan inverse of u plus c, and what u was right here, x plus 1. So when you plug it in, the final answer is tan inverse of x plus 1 plus c. And that was nice. Very straightforward to do, right? Let's go a curveball again. let's go a curveball here where you have something like this. Integral of 1 over square root of 1 minus 9x squared. So this is where it's going to get very tricky because the rules need to be bended for this, okay? The rules just want to give you a basic motivation here. But if you go back to the idea, right now what you see is 1 minus 9x squared. Okay, so when you see 1 minus something squared, what you should lean towards is that 1 minus sine squared of t is cos, cos squared of t. So that's going to be helping us, okay? We got to make sure we keep that in mind. Not the dt. Why were there? My bad. So we know this. It's going to be true. So now if you were to like resolve this expression slightly to help you out, what you would see is you can write this as 1 minus 3x whole squared. Okay? And we want to make it to a single term. If you correctly follow along, what you should see is if this inside part was sine t, what you'll end up with is 1 minus sine squared t, which could be resolved, right, into cos squared of t, isn't it? So what I would do here is I would take this opportunity and substitute that whole inside part as sine t. So I'm going to use trig substitution here. I'm going to say let the 3x inside be sine t, because then it will help me solve my expression very easily, right? Let it be this, and then once you plug it in, you can easily find the bottom to be resolved into square root of, when you plug it in, you get 1 minus sine squared of t equals to cos squared of t. So this will give you a cos squared of t in the bottom. But we still have to figure out the dx, right? This dx was supposed to be there at the beginning. So we have to make sure we substitute for that. So over there, when you see here, your expression is not that easy to evaluate. But what you can do is you can isolate for x first. You can say x to be equals to 1/3 of sine t, right? And then from there, dx is just going to be equals to derivative of sine is going to be cos t over 3. Good. And then this times dt. So this is going to have a cos t over 3 dt. Nice. Let's try to simplify this a bit. And what we're going to get is 1/3 could be factored out. On the top, you're going to have a cos of t. Square root of cos squared at the bottom will just give you a cos t again. dt. This goes away. Magic. And then you'll be left with 1/3 of t plus c. So now from there, isolating for t could be kind of tricky. So we can come back to our expression. And we can go back down there and see that if 3x equals to sine of t, then t is nothing but sine inverse of whatever's on that side, so 3x. And that could be plugged in to give your final answer to be 1/3 sine inverse of 3x plus c. Okay, and that is one of the examples of, using this weird way. The motivation here is to actually figure out what needs to be that thing. Okay, so we can start off with an ugly expression as well. Let's start with an ugly expression, try to see how we can deal with that. So we're going to do the same kind of form. Let's say dx over square root of 5 minus 4x squared, something like that. Okay, which is very hard to identify. So now what I want to do though is I want to make sure I see my forms correctly. Okay, the motivation is to have 1 minus something squared, right? And then something needs to be turned into sine. So first of all, we have to make a 1 there. So whatever that constant is, you got to take it out of the window. Okay, so what I will do is I will just explain in a second that this could be written like that. 5 factored out, you'll be 1 minus 4 over 5x squared, right? You can factor out the 5 out of this thing. And now you have a 1, so you can start to think about, okay, 1 minus something squared is leaning towards, putting sine there. So if the inside part would be a sine, would be really nice. So let's try to see what do we have in the square at least. So when you're looking at 4 over 5x squared, you can write this as square root of, well, I'm just simplifying a square root. I'll plug it back into the integral in the denominator later, okay? I'm just trying to resolve the expression first. So 5, 1 minus, I want to combine them whole under the umbrella of a square. So what I do is I just, 4 square root is 2 over square root of 5 x whole square. So if you see, this expression has no difference in between each other. All I did is just wrote them in that form. Okay, so now what I have is square root of 5 and then 1 minus 2 over square root of 5 x whole squared. Right? So now if I put the resembling form down there, you have 1 minus, you know, sine t whole squared. If you see that, then you want to make sure that these two are matching up. If that inside was equals to, you know, that side, then I can easily resolve this expression. So this is where I find my motivation to what I should substitute. What I would do is I'll put the 2 over square root of 5 x as sine t. If I do that in this expression, what I'm going to get is square root of 5, 1 minus sine t whole squared, and 1 minus sine t is going to be cos squared of t. So I'm going to end up with square root of 5 cos squared t. Nice, that's resolved. But because there was a dx here on top, we have to make sure I substitute for that. So let's try to find dx from this expression down here. Okay, when you move it over, you're going to get, you know, x to be equals to square root of 5 over 2 sine t. Just rearranging it, right, a bit. So knowing that, you can find your dx to be the square root of 5 over 2, just stay there, right? It doesn't change anything. And then derivative of sine is going to be cos of t dt. Well, we got every piece together. This belongs in the denominator, and dx and will be substituted in the numerator, so we're going to get this. So square root of 5 over 2 cos t dt all over square root of 5 cos square root of t. When you want to resolve this, you can factor the square root of 5 over 2 outside. You'll be left with cos of t dt on the top. And square root of that expression will give you square root of 5 times cos of t dt. Basically cos of t. Now here again, these coses will go away. So this square root of 5 and that square root of 5 will go away. So you'll be left with 1/2 dt, which is just going to be t over 2 plus c. That's the expression. Now we have to plug in for t. Remember, we had this expression there. So this expression will tell you that t is nothing but sine inverse of basically all of the mumbo jumbo here, right? So there'll be 2x over square root of 5. This is where it looks ugly, right? So when you find that t there, you take it in, you plug it in there. So the final answer for this integral, I'm gonna get rid of this space here. The final answer to that integral is just going to be sine inverse of 2x square root of 5 over 2 plus c. That's literally me plugging in t in terms of that and then just taking it back over there. Okay, and that's pretty much how you tackle any kind of ugly ones, right? And one last example is where I want to focus a little bit more, okay, because there's some extra things that you need to have in order to solve some problems, or, you know, the trig substitutions one. So there's one more identity that I want to make sure you guys remember. These are called the half angle formulas. What they do is they will help you convert the sine squared of something and cos squared of something into something that you can easily integrate. Okay, so from there you have to remember this: sine squared of x could be written as 1 minus cos of twice of x divided by 2, and then cos squared of x could be written as 1 plus cos of 2x divided by 2. They're pretty standard. It's good to you know, keep them handy. You can remember them, and it'll help you solve problems in a much faster way. Okay, whenever you encounter you know, squared of cos or squared of sine, the best way to actually resolve this would be to use, the half angle formulas. So there's one example that I want to cover up, which is kind of bum a lot of people out, which has a squared of some identity there. Let me try to find up exactly what that number is, and then we can start off solving it. The expression was going to be, can't seem to be able to find it. Just give me a second. That was on a web work. So let's think about this. So I think I remember that correctly. It was dx over x squared plus 2x plus 2 whole squared. Okay, so you're gonna be ending up with this kind of expression there. When you see this, the first motivation is try to see if the quadratic is easy to factor or not. Okay, because whenever we see a quadratic in the denominator, we want to see if we can factor it out or not. So in this case, you see it's not, because we've been working on this example for so long now. So the only other way for you is to actually complete the squares. And we know by completing the squares, x squared plus 2x plus 2 from the previous examples could be written as x plus 1 whole squared plus 1, right? So I can substitute it back in. My new integral will look something like this. Dx over x plus 1 whole squared plus 1, and then outside you have a whole square. Okay, so now in this case, if I compare it to some standard form, I think I'm leaning towards tan t plus 1, right? So what I want is I want this inside to be tan t, right? So this is where I draw my motivation to do the substitution here in the trig way. So I will say let x plus 1 equals to tan t. And from that expression, what I can do is I can find my dx to be, the derivative of tangent is going to be, if you move that over, so I can write x equals to tan t minus 1, and then take its derivative, you get dx over secant squared t dt. Nice. So once we have that expression there, we can plug it in and simplify my integral to be dx over, this whole thing will become tan squared t plus 1, which will resolve to be secant squared t. My bad, I need to get rid of this thing. So secant squared t whole squared. And then at the same time, what we have is here is the dt expression, right? So dx could be substituted like that. So we have secant squared t dt. So when you resolve this, you're going to get a secant squared on top and a secant to the 4 at the bottom. In this case, the magic happens with partially, right? You got to cancel this. You will resolve that to be a squared. And what you're going to end up here is 1 over secant squared t dt, which, if you know a little bit of trig, could be written as cos is just 1 over secant. So what you're going to end up with is an integral of a cos squared t dt. So simplified in form, it's that way. Now, once we're reached to that spot, we don't know how to integrate cos squared. So this is where this half angle formula will help in to convert that cos squared into a regular expression. So because of that, I can write this integral to be 1 plus cos of 2t over 2, right, dt. I can split them up into 1/2 plus cos of 2t over 2 dt. And this integrals are going to be t over 2. And integral of cos of 2t is sine of 2t over 2. But because you have another 2 here, so it's going to be over 4. This is using the chain rule of integration, okay? If you want to brush up on that, you can look in the previous parts where we talk about a chain rule, okay? So this is where the chain rule integration comes in. You have this expression, and that's pretty much the answer. But still, you have to simplify the expression. Remember here, when you chose your t to be this, your actual value of t is nothing but tan inverse of x plus 1. Knowing this, you got to substitute it back into the expression. So your answer will be tan inverse of x plus 1 over 2 plus sine of twice of tan inverse of x plus 1 divided by 4 plus c. And that is supposed to be the answer. Of course, there's still some extra scope of simplifying this portion here. But my point here is to actually convey the idea of trig substitution in helping you solve the problems, right? So that is just my idea here. That's what I wanted to focus on. Another one simpler example, because we're dealing with a lot of quadratics in the denominators. Let's try to deal with a quadratic that's in the actual numerator, okay? So some standard forms like this would require you to use trig substitution, something like, you know, square root of, let's say, 256. 256 minus, let's keep it easy, x squared dx. So when you see something like this, what do you think you should substitute it here? So first of all, you need to make sure that you want to, you know, use the rules that I mentioned, or you can always use the motivation. In this case, the motivation is you have 1 minus x squared form, right? Because then 1 minus x squared form could be substituted with a sign in order to resolve that to be a cos. Easy. So what do I want to do though, is I want to make sure I have a factor of 1 there first of all. So that will be written as 256 square root with the inside of 1 minus x squared over 256. Right, I can factor 256 and then I can bring it out of the square root because square root of 256 is 16. So I can write it as 16 square root of 1 minus x squared over 256, right? So this expression is what I'm at right now. Now what I want to do is I want to combine, you know, see what substitution is going to work. So I'm going to write it here in a simplified form, 16 square root of 1 minus. So if you want to combine this under the same square root umbrella, what you want to write is x over 16 whole squared, because x over 16 whole squared is nothing but x squared over 256, right? So knowing this, you can write it to the resembling form of 1 minus sine t whole squared, right? And then what you want is the inside to be equals to sine t. So basically x over 16 equals to sine t, which will tell you that x equals to 16 sine t. From there, if you isolate for your dx, which is coming in from there, you find that you get dx equals to be 16 cos of t dt. And let's bring it back in and then see what we are ending up with. This 16 could be factored outside. So have 16 outside. This whole scenario will be 1 minus sine squared t, because that's what we're actually substituting for. So I'm going to be left with just a cos squared square root, right? So I'm going to get square root of cos squared t times 16 cos t dt. That's the expression for dx. This 16 could be factored out as well. So I'm going to be getting a 16 times 16 outside, which is just 256. Integral of cos t, because square root of a square cos is going to be cos t, times another cos t that's here because of this integral dt. So I'm having a 256 integral of cos squared t dt. So now here, because I cannot integrate cos squared of t, I need to use the half angle formula. So I can write this as 256 integral of 1 plus cos of twice t divided by 2 dt. Okay, and then this we already computed in the previous go is 256 factored outside. This will be t half plus sine 2t by 4 plus c. And now because of here, the expression that we had our sine to be this, I can plug it in. I can choose my t to be sine inverse of x over 16. So when you plug it in, what you're going to get is the last answer is 256 times sine inverse of x over 16 over 2, because that's the value of t, and then plus sine of twice of sine inverse of x over 16 divided by 4, and of course a plus c, which I don't have a space to write here, so I'm going to add a plus c on top. And that is how you solve this question, right? So anytime when you see quadratics which could be not factored, you should always lean towards completing the squares. And then from this point onwards, you can start, solving more complex problems in the future. I'm just going to give you a brief here. Okay, if you see a quadratic like this, the one last example, this is extra. Okay, that's a bonus of this. If you made it this far in the video, you're going to get this bonus. So the moment you see something like this, integral of, let's say x squared plus 2x plus 1, right? The moment you see this, this is going to be easily factorable. So you're going to get x plus 1 whole squared, right, dx, which will be resolved to integral of x plus 1, because square root of squares is going to give you that. And this could be easily solved to find the answer, right? This will be s squared over 2 plus x plus c. Easy. Now, whenever you see something weird happening in this place where you can't factor it, your motivation should take you towards the trig substitution, right? So if you were to have something that you can't factor, why don't we just go with this guy, the one that we've been working on? You can complete the squares just like we did in the previous questions to x plus 1 whole squared plus 1 dx, right? And then you can substitute trig substitution here, because this looks like tan squared plus 1. So basically you want your x plus 1 to be tan t, and then what you're going to resolve is going to be a secant, right? So you know how to get this. But what if you wanted to find a shortcut formula that's going to help you solve any quadratic inside a square root like this? So the question that I'm putting here is this guy. Is how would you solve this generic quadratic plus bx plus c dx, where a, b, c are constants? Okay, so ABC could be anything. In the previous case, the ABC, A was 1, B was 2, and C was 2, right? That was just a specific case. But what if we keep them as ABC constants and then try to see if we can actually simplify this expression even a little bit or not? Okay, the motivation here, because you see a quadratic in there and you don't know how to factor it, and the factors are going to be disgusting. So the better way to do that is to actually solve it using trig substitution. So why don't we just complete the squares? And the method of completing squares requires you to have a coefficient of 1 for the x squares. What I'm going to do is I'm going to factor the a outside. So we're going to have this. I'm just going to complete the squares and then put it back in, okay? So you're going to have ax squared plus bx plus c. I can factor the a outside of this, so I'm going to be leaving with x squared plus b over ax plus c over a, right? Knowing this, how would you factor, kind of like compose this scenario? Is you have x squared plus b over a x plus c over a, and in the completing square form could be written as x squared plus 2x times something plus that thing squared minus that thing squared, and a plus c over a, because that's the thing that's out here. So now what should be multiplied here in order to get b over a? So you kind of have an idea that should be b over 2a. When you multiply by b over 2a, what you're going to end up is essentially b over ax. So you're going to have b over 2a here as well, b over 2a here as well. Right now it's becoming very hideous already. And that's the point I wanted to make, right? It becomes very nasty as you go. But as long as you have faith in the method, it will work out. So I'm just going to give you partial steps here, and I'll let you continue from that point onward. In this case, once you write it in the completed square form, this will become not x, plus b over 2a whole squared. And then this could be resolved. So you have minus b squared over 4a squared and plus c over a. So if you wanted to resolve this expression, what you can do is you can say minus b squared over 4a squared could be written as that, and then plus, to have the same LCM, you're going to have to multiply by 4a at the bottom. So you have a 4a and the 4a on the top. So this expression is just basically 4ac minus b squared over 4a squared. Very crazy. Okay. Knowing this, that this quadratic could be, you know, completed squares to be x plus b over 2a whole squared, and then a plus of 4ac minus b squared over 4a, which is another constant, which I'm going to call, you know, the capital K for some reason. I'm going to call the capital K because I don't want to keep on writing this expression. So now my expression would be simplified to be like this. So the a was factored out because remember we factored out this a. It wasn't even in the picture, so we only expanded that thing. So this is looking like this. So a times x plus b over 2a whole squared plus this k. So my expression now in the integral will look like this. This squared and a plus k. So from this, what I can do is I can take the square root of a outside. So I have a square root of a. This is algebra to the max. Okay, it's going out of the roof. A whole square plus capital K. So now you have a perfect squared form and you want to do a trig substitution here. And the trig substitution is leaning towards something squared plus a constant is telling you want that inside to be a tan, right? So you want it to be a tan. Now in this case, how would you even think about it? Because you don't have a 1 there. You still have to keep a 1, right? So let's take that 1 first. Square root of a. And I factor out the k outside that thing. Now, so when I do that, I'm going to be left with, you know, x plus b over 2a. Okay. I'm going to just try to like make it nice. With a k at the bottom and a plus 1. Okay, so we got this, and then this is the expression so far. Much crazy. But I can combine them under the same umbrella by doing the square root of k and extending this bracket all the way down there. Now this is where the hideous part comes in. You want to compare this to be a tan t plus 1. As if everything else wasn't, you know, helping you out. But yeah, you got to make sure that you see that pattern. So basically x plus b over 2a over square root of k is supposed to be plugged in as tan t. And when you do that, surprisingly everything else is a constant. You know that dx equals to dt. So there's no trouble there. In this case, when you try to calc that, so dx will just be equals to secant squared t dt. So this maniac could be converted into, if you factor the square root of k outside this as well, so we square root of ak, right? And in the integral you have left with the square root of tan squared t plus 1 will be secant squared t, and you have a secant squared t dt outside, which will leave you with a square root of ak, and a secant squared will be secant. There's out one outside, so you have a secant cube t dt. Oh boy. And this is still supposed to be solved because secant cube t is something you can't compute right away. You got to use other methods. But the point here is the simplification will still work. Okay, and this is the general approach for solving any of the quadratics that you see. The point that I wanted to make with this example is not to teach you anything, and don't expect this to be on your final or exam anyways. But simplification is so flexible that you need to keep the motivation in your brain. Okay, the point one idea is that when you look at this trig identities here in the beginning that I mentioned, since we began, okay, the point is that you want to make sure you have 1 minus sine squared form to get cos squared, 1 plus tan squared to get to secant squared, and secant squared x minus 1 to get to tan squared, right? So you can condense one single expression into that. You can use these rules if you want to, or you can use the motivation that we just talked about in the very first video of this series. And I hope you'll be able to solve all the problems, right? And if at any point during this time you encounter some problems that you can't solve, always feel free to reach out to me, and I'll be more than happy to help for any of these things. And thanks for watching this. I know this was probably the longest one, but yeah, thanks for holding up. If you have any questions, please let me know.